We've seen so much extreme weather recently that it's hard to keep up with all the records that have been broken. In fact, in 2021, 10.6% of all weather stations recorded record temperatures. It's easy to blame global warming, but extremes have not only become hotter and drier, they've also gotten wetter, snowier, windier, and colder. So we have to dig a bit deeper to understand why and where these extremes are happening so that we can prepare for what's actually coming our way.
In this episode, we're going to explore groundbreaking new research that reveals one common factor connecting almost all of these extremes and even suggests what we can expect in the future.
And to do this, we'll start by zooming out, way out to the troposphere. Then we're going back in time by drilling into Greenland's ice sheet to uncover clues about our very uncertain future.
The changes we experience in our climate and weather are fascinating and definitely overwhelming at times. But the more we understand about what's happening both today and down the road, the safer we can be. And if you want to see more content on changing weather and how to prepare, give us a like and subscribe. Let's dive in.
The jet stream is this meandering, waving, buckling band of west to east moving winds that are situated in the mid-latitudes. And they're really important for us as humans in our day-to-day lives because the jet stream seems to dictate much of the weather that we experience. So any change in weather that we have actually is related to how these upper atmosphere winds are changing.
And as we'll see, shifts in the jet stream connect most of the extremes we saw in 2021.
The jet stream forms where warm air from the tropics meets cold air from the poles, and it moves weather systems from west to east due to the rotation of the Earth. Without it, we'd see far fewer changes in our daily weather.
Exactly how much effect climate change has on the jet stream is hotly debated, but Judah Cohen is a climate researcher whose work focuses on this exact question.
Strength of the jet stream is very much dependent on how large is that temperature difference between the equator and the North Pole. The Arctic is warming 2 to 3 times faster than the rest of the globe. So that means that temperature difference is slackening or weakening. With a weaker temperature difference, also the jet stream is kind of weakening or slackening. The winds are not as fast. Now that I think everybody agrees on. But there is kind of this new idea that really didn't exist 10 years ago, that this weaker jet stream also leads to slower moving weather systems and also a more amplified or greater waves inside the jet streams. If the waves in the jet stream have much larger north to south extent, there's much more vigorous mixing of air masses. So you bring cold air from let's say the Arctic or in Alaska and Canada, bring it down to Texas and Georgia, right? And so it's very anomalous. If it's cold in Fairbanks, they can handle it. They're used to it. When that same cold air is quickly transported into Dallas, Texas or Atlanta, Georgia, they're not used to it, and it causes havoc with our infrastructure and human lives.
This theory may be new, but 2021 made a pretty convincing case. In fact, it's hard to find examples of major weather events from last year that aren't connected to the changes in the jet stream.
The Texas deep freeze was caused by the jet stream becoming so wavy that it brought Arctic air from the poles to the southern U.S. Later, the jet stream was so coiled and slow over the Pacific Northwest that it trapped a high-pressure system over that region, allowing hot summer sun to heat stagnant air to new highs. A similar pattern caused flooding in Europe and fires in Siberia. Then Hurricane Ida slowed as it hit the Gulf states, and instead of being pushed offshore by atmospheric winds, it was blocked by a high-pressure system and dropped record rain over the eastern U.S.
So, how do we build resiliency to climate change? And it really will come down to a large part changes to extreme weather. And again, extreme weather is very much strongly connected to changes in the jet stream.
Okay, and that is happening more because of Arctic amplification, correct?
So that, this is a controversial idea. That's an argument that I'm making.
And Judah is not alone. So We'll see in the coming years how this debate plays out, but it's not just wind direction and speed that can change. In fact, the entire system might be migrating, which could mean even more significant and long-lasting changes to our climate at ground level. Matthew Osman from the University of Arizona's Climate Systems Center recently discovered chilling data that suggests the jet stream is moving north.
If we want to understand how climate change is going to evolve in the future, we need to understand how and why it has changed in the past.
Okay, so how do you figure out climate changes and jet stream locations before satellites were documenting them?
So in this case, what my team was able to do was to collect measurements of glacial ice from across Greenland and combine those measurements together in order to dissect properties of the climate that are related to changes in the jet stream.
By doing this, they were able to find changes in the jet stream's position and intensity going back 1,200 years. And they found evidence of big changes.
Going back 1,000 years into the past, we see that changes in where it's positioned across space can be on the order of 10 or more degrees latitude. So this is a lot of area that the jet stream is covering on these really long time scales. And this, of course, has big impacts on changes in weather that we've seen over the last millennium.
Over the last 100 years, we've been emitting greenhouse gases into the atmosphere, causing the climate to warm. And remember, the jet stream is created where warm southern air meets cold northern air. And if the Earth warms, then the place where those air masses collide might move north because there's less cold air.
So what we've seen is this slight trending of the jet stream's position towards the north over the last 40 years, but it hasn't been clear whether or not this is driven by natural changes or whether this is human-caused.
And one convincing way to separate human-caused jet stream migration from its natural variability is that the jet stream's average location goes outside of the historic range.
And what we can do is actually compare projected changes in the jet stream that we get from models with the range of variability that we see in our reconstruction. This is essentially the range of natural variability. And what we see is that for high greenhouse gas emission scenarios, we might find ourselves in a position where the jet stream becomes effectively distinct from the range of natural variability within the coming decades by as early as 2060 CE. Observations that we have from satellites, as well as estimates of the climate system that we get from models, both agree that the onset of changes in the jet stream's position has already began. It probably began about 20 years ago in the late 20th century. And this is really important because when we start to think about climate extremes, right? So extremes in precipitation or temperature, we care about where the edges of those variations exist.
This is because as the jet stream migrates beyond the limits of its historic range, we're likely to see even greater extremes in our climate than we're used to.
If we continue to emit greenhouse gases, we will see a migration of the jet stream further and further to the north. And as we push the North Atlantic jet stream outside its natural range, we will see consequences in where the temperature extremes as well as precipitation extremes fall for the places where you and I live today.
If this pattern continues to play out, places like California and much of the American Southwest will keep getting hotter and drier as the jet stream delivers less and less moisture from the ocean, while some more temperate regions like the Pacific Northwest will receive even more moisture than they currently do.
This means many already dry regions becoming drier and wet regions becoming wetter. And the same pattern would likely hold true across much of southern and northern Europe. Our understanding of these changes is still evolving, but Matt and Judah's work underscores the need for preparation. And I, for one, feel a lot better when I understand and when I'm ready for what's coming our way. For a deeper dive on how to cope, check out our previous episodes on drought, flooding, and winter weather. And finally, we'd love to hear what you think about this subject, as well as what other weather and climate topics you'd like for us to cover in the future. Until next time, stay safe.